Should we start?
Yeah.
Okay, welcome to another member seminar. It's a pleasure to have Professor Jinsong Wu from BIMSA, who is going to talk about quantum Fourier analysis.
Okay, thanks for Aten's introduction, and thanks for the committee to invite me to give this talk. What I'm going to talk about today is the framework of quantum Fourier analysis. I will briefly introduce this framework. Actually, it's a big program to me. So I'm going to explain Fourier analysis and quantum. Okay. Currently we don't have too many members in this program. We have Arthur Jeff from Harvard University, and Chenlan Jian from Hebei Normal University, and Zhengwei Liu from Tsinghua University and BIMSA, and Lin Zehuang from BIMSA, and me. You know that the classical Fourier transform was studied by Joseph Fourier in about 1822, right? And he used it for solving the heat equation. It is very powerful. We briefly introduce the definition of Fourier transform here. It is an integration of f together with a special function e to the power negative 2 pi its. It has a lot of important properties. Here we only list some of them. The first one is the derivative. When we take the derivative inside, actually we will get s outside. Okay. And we also can differentiate the Fourier transform. But there's another equation. This is very important fundamental for the Fourier transform. And the second one is also very important. It's called the Panchara formula. It says that the two norm of Fourier transform is equal to itself. Okay, in classical Fourier analysis, this is actually is very important and it's not easy to prove. Okay, because it's the function f. If you just read the definition, f usually should be in L1. Okay, that is the difficult. That is why we should use the Schwarz function. But here I'm going to skip these details and just go to some rough idea. The next, if we change the norms, usually we would like to use one norm and two norm, right? But there will be p norms, and p could be from 1 to infinity. So this will give us the Hausdorff-Yang inequality. Hausdorff-Yang inequality, in the usual Hausdorff-Yang inequality, the AP here is actually 1, it's not AP. That is why we put AP here. This is called the sharp Hausdorff-Yang inequality. It's a highly non-trivial. Actually, it's proved by Buckner in 1975, I think. And he used a non-trivial proof, which first use the 2-point inequality, then use an approximation. Okay. Separate for some function. What do you mean? Oh, the sharp means this is the optimal. This is the best one. So if you put it, that means this inequality can be reached by using Gauss function. Because if this is simply 1, then for the number p from between 1 to 2, then Gaussian function is not reach it's not reach the usual one. Okay, so that is why they guess this AP by inputs the Gaussian function, and they guess this should be the sharp one. Then they prove it, and the proof is non-trivial. And later in around 1990. No, this is the condition. This is the condition. P is from 1 to 2, and PQ are conjugate. Yeah, and AP is this constant. Yeah. So the non-triviality is the constant. Yeah, you can easily obtain this trivial out of inequality by using further inequality. Actually, maybe you can go directly. Yeah, you can use the absolute value inequality directly, and then use the interpolation theory, and you will get the trivial one. Okay. But for this non-trivial one, you cannot use interpolation theory. So for this Fourier transform is it can solve differential equation and prove the central limit theory. Yeah. And what I would like to say here is that we have parameter here, the Q. Then we can differentiate this P or Q at the point P equal to 2. Because at the point P equal to 2, this is an equation. Then we will get another inequality for the Hirschman-Berkner uncertainty principle. It's very important in quantum mechanics because it actually implies that Heisenberg uncertainty principle, and that says that the position of the monoid is the answer has uncertainty relation. Okay. So this is from the Fourier analysis point of view to look at the uncertainty principle. It also has a lot of variation of uncertainty principles. The other way to look at the Fourier transform is the convolution. Okay. For two functions f1 and f2, we can take the convolution in this way. This is the standard way. Okay. The relation between convolution and the Fourier transform is using this equation. That means the Fourier transform interchange the convolution and the multiplication. This is also very important because this indicates that on the functions of on R, there are two multiplications actually. One is the convolution, the other one is the point-by-point multiplication. So it also has this sharp Yanqi inequality. Okay, and the constant here is non-trivial. You can also use the interpolation theory to get a trivial one. And for this one, you cannot use the interpolation theory. So that is why it is non-trivial. For now, there are a lot of proofs for this inequality. But actually, as I know, for the Hausdorff-Yang inequality, there are only two proofs. If you reverse the sign, reverse this inequality, we will get the reverse Yang inequality. Okay, if we consider the extremizer of the two inequalities, we will say that the Gaussian functions are the extremizer or extremal pair. So that means the Gaussian function is very important. Not just important in this inequality, it's also important in probability exactly. Okay, because it is the limit of identical independent distribution. Okay. Both of them should be Gaussian. Yeah. But there will be some limitation, some restriction on the coefficient. Actually, if you consider the Gaussian function, there should be a squared plus bx plus c, right? We simplify it. We just consider this one. Okay.
First Young quality satisfies the sharpening quality satisfies reverse number.
The sharpening? No, this is different things. You say that the condition is different. This RPQ is less or equal to infinity. This is greater equal to 0. And here, this is from 0 to 1. You see, this is that yeah, the complete different inequalities actually. Yeah. So usually we, for harmonic analysis, there are a lot of such cases. If you can find an inequality, then you can consider the reverse one. Okay. That corresponds to the developing spaces, right? Yeah. So can you explain what
dual to each other?
Actually, this is similar to the Herder inequality. You say that Herder inequality actually also has the reverse one. So it's I can tell you after this talk because a little trick here, a little technical here. Okay, because it's not like the usual one. We consider the dual space, but we do not consider that directly. Okay, because of this convolution here. If you just think about the Herder inequality, then you can use the duality directly. You see that if you use this change this convolution to multiplication, this actually is the usual one, the Herder inequality. You see that, and for the Herder inequality is not does not satisfy this condition is quite different. So there's something changed actually here. That is why we cannot deduce this directly. Okay. We say that the Gaussian function are the extremizer of the sharp Hausdorff-Yang inequality, the extreme pair of the sharp Yang inequality. If we differentiate the Hausdorff-Yang inequality, we will get Hirschman-Beckner uncertainty principle. What if we differentiate the Hausdorff-Yang inequality? You see that the Hausdorff-Yang inequality also has parameters RPQ. If we differentiate Hausdorff-Yang, if we differentiate the sharp Yang inequality, we actually will get the entropy power inequality, which is very useful in information theory. Okay. And it's more important that its extremizer is also Gaussian function. Okay. So this indicates that the Hausdorff-Yang inequality is very important. That is why we people want to generalize the Yanqi inequality. Okay. When they just generalize it, they will get the Brass-Campbell-Lieber inequality, which is extensively generalized. Okay, and its extremizer is still Gaussian functions. So there are a lot of inequalities inside. In a summary, we can write this table. So for the classical inequality, the core actually is the Brass-Campbell-Lieber inequality. It generalizes almost everything. That is why we would like to study Brass-Campbell-Lieber inequality in a general way. I mean, here is in a quantum way. Okay. You say that the entropy power inequality can imply the log Sobolev inequality. And the log Sobolev inequality is equivalent to hypercontractivity. And hypercontractivity is very useful and powerful in the quantum field theory. Okay. So in my picture here, I just list the connection between Fourier analysis and the information theory, differential equation, quantum mechanics, quantum field theory here. Actually, it has a much more connection with the other field. Okay. What I want to say here is that the classical Fourier analysis is very important and is very powerful. Okay. And it has a lot of connections with the other field. So if we go back to the definition of Fourier transform, we say that there are actually a duality between R and itself. That means R is self-dual. Can we find more duality? Of course we can, right? This is very simple. If you consider this finite abelian group, then you can say that then is duality to itself. Is dual to itself. And if you consider Z is dual to S1. And if you consider R is dual to itself. And the Fourier transform is very easy to write out by using this E2 2 pi I TS. So is there any other duality? If we consider abelian case, we will have local compact abelian groups. Okay, because you can correct this duality by using correct function. Okay, so is dual is still is still commutative. It's still commutative. So we can go further, right? We can consider finite group or compact group. Then we have this compact group. What is duality? Then there's a simple way. You can consider its irreducible representations. If you consider all its irreducible representation, you will get its dual. But this is not the all the way. It's not the final case, right? Because if you consider the free group, you say that if you can give a free group, if you consider its irreducible representation, then you say that the irreducible representation cannot determine it. It's highly non-trivial. And there are a lot of groups like free group. You cannot use the irreducible representation to determine it. Okay. So there should be a more general duality to study it. For such case, we always can get one side is commutative. And this is very helpful because we can actually use the function property. The advantage for function is that you can take the multiplication trivially, point by point. But for general case, we cannot, because we will get a matrix, right? Usually we'll consider the operator. So if we extend it, we will get the non-commutative duality. Here, I only consider the Phys algebra version. Actually, it's the unitary version, but there are also some algebra version. Okay, because for the algebra version, it's really hard to do analysis. But for Phys version, or maybe later we'll call the unitary version, it has a positivity, and we can do the analysis. So this the first one is the Cas algebra. It's introduced by Adv Math in Swash. It generalizes the duality of group. Okay, and you can further generalize to the compact quantum group by oral knowledge. I'm not going to give the definition of this notation because the notation is quite long and it's too technical. But I'm going to say that there are actually a lot of versions of non-commutative duality. Also locally compact quantum group, they all can be infinite case. But here I'm going to emphasize is the Jones subfactor theory. To study Jones subfactor theory, we are going to use the subfactor Func algebra. And for subfactor Func algebra, the definition is a little long, and I'm not going to give the definition. But I would like to say that it almost generalizes all classical symmetry. Okay, it's almost so. I would like to use almost because there are always some special case. So in a summary, we have the usual way, the classical symmetry, and the quantum symmetry here. But commentary we have to use. We don't have the rigorous definition of quantum symmetry. Okay. So here, when I say the quantum symmetry, I simply mean the simple the subfactor. Okay, simply mean the subfactor. So for finite group, for finite abelian group, we say that it is finite, and its dual is also finite and commutative. And for real line and locally compact abelian group, it is infinite. Okay, because the element inside is infinite, but itself is commutative, and its dual side is also commutative. So this is the classical one. If we simply consider the group case, then we say that one side, the finite group, usually we do not require its abelian. Then one side is commutative because it's a group function algebra. The other side is its representation. That usually is non-commutative. Also consider the locally compact group like a free group. This part is much harder because for both sides, they are non-commutative. So most classical technique cannot be applied here. So we should develop some new techniques. So our main interest will be suffacting. Suffacting is developed by Jones in around the 1980s. It connects a lot of fields like quantum group, quantum information, statistical physics, lower dimension quantum topology, especially the knot theory and the tensor categories, operator algebras, quantum field theory, representation theory. So when we say quantum Fourier analysis here, it is a subject of studying Fourier analysis on quantum symmetry. Actually, we are mostly interested in suffacting now. Okay, then we should introduce the Fourier transform. Actually, when in around 2016, I went to Vanderbilt and I want to know some subfactors. And I found that in subfactor theory, there's a Fourier transform. It's very amazing to me because I know that there are a lot of theory about the classical Fourier transform, but it seems that it's not too much theory in the subfactor theory. Okay, and we found that for finite group, this Fourier transform is exactly the Fourier transform, the classical Fourier transform, but it has a nice expression because by using subfactor planar, it has this topological interpolation. Okay, it actually is 19-degree rotation. In the other way, if we put this as shaded, this is unshaded, then this actually is the interchange the shaded region to the unshaded region. So it coincides the classical Fourier transform, because for the classical transform, if you take the power 4, you will get identity. And it's easy to get its eigenvalues. That will be 1, -1, I, and -I. Okay. And that is how we can get the eigenspace actually is determined by the Hermitian polynomial. But here, we only have this abstract expression. Okay, it has algebraic formulation here. It's usually it's not easy to use. I simply interpret this here. This E1, E2 are Jones projection. Okay, it gives the structure of this Jones theory. I'm not going to give the details of this one. I would like to say the simple idea is that is to take the rotation, or other way is to change the colors. Okay. But here, if we take the value of the closed loop, we will get this value delta. In the quantum theory, we say that this delta is non-trivial. Usually, if you use the group case, this delta actually will be an integer. But here is not an integer. Here is for group case, this is the square root of integer. Okay, Jones index actually is the integer. But here is some special number. It's 2 cosine pi over n. N is from 3 to infinity. And this is for the number less or equal to 2. But for the number greater or equal to 2, it takes all values. So this is completely different from the class case. Okay. So this delta square is the Jones index. And this also has a topological meaning. It is the value of closed loop. For this Fourier transform, we also have the Pan-Cherry formula. The Fourier transform, the two normal of the Fourier transform is equal to the two normal of itself. Yeah, yeah, exactly. Yes, yes, you're right. Yeah. Yes, yes, yes.
Think of X as a kind of a quantum state.
Yes, you can say that. Yeah, it could be wave function. Pardon? What is the wave function? Yeah, it's linear. It's considered operator here. Usually, if it's finite, then it's simply the matrix, it's the element in the matrix algebra. But it could be more complicated. Yes. Yeah. For finite index, usually we consider finite index. Yeah. If you use the category theory, then you can also consider it as the Morphy space, element from the Morphy space. Yeah. If it's finite, then you usually use matrix. It's the element in the matrix element. It could be infinity. Okay. If it's infinite, then we have to use operators acting on the field space. Yeah.
X is an operator.
Yeah.
Those things coming into that box are a state, input and output state.
Yeah, you can say that. Yeah, if when you say states, usually we consider this is a positive operator, right? Yeah. And you also have to a lot of requirements for this state. Because in operator algebra, state actually is a normal linear function. Yeah. And positive normal linear function. Yeah, with this planetary formula, yeah, it is. Yeah. Oh, this is condition equation. Conditional equation. This is non-commutative conditional equation. Yeah. Yeah, if I want to explain the notation, then I have to use an hour to explain this notation. So I'm going to just roughly introduce the idea. Yeah. Otherwise, we will say a lot of technical things. Yeah, if you consider the group case, then yeah, it will give you the examples. Like if you just actually change the group function to its representation. Yeah. So it can be function actually. This X can be function for some special case. It can be the function on the F. Yeah. Then if you take the Fourier transform, then there will be a matrix on still. Okay. Because it still actually is an algebra. It's not a function. Yeah. Yeah, if you consider endomorphism, yeah. Well, imports. What do you mean? What do you mean by imports?
Says why is it two things come to X and two things X? Why not one? One is just when you have operation instead. If you input, you get something.
Yes, yes. But you are right. Actually, we are not only have this two. Actually, we have n, but we just write two here because of some the complexity of this theory. Yeah. So for the suffix theory, actually, it's not just two. It could be one. It could be one. Actually, yeah, yeah. So my warranty definition here, I actually use n strings here, but I think that might be too complicated. So that is why I put two here, because two is the first non-trivial one. If you just consider one, then this is trivial. You say that this is the flip of this diagram. Actually, it's simply it's automorph. It's an isomorphism, right? But here, if we consider the product, we say that this is not an isomorphism because the product changes. The one side is product, the other side, the product actually is the convolution. This is similar to the classical one. Yeah. Actually, we have more structure here. Then we will have the Hausdorff-Yang inequality. It's very similar to the classical one. We also have this Q from 2 to infinity, P is from 1 to 2. But the coefficient changes. You say that in the classical one, this is AP. And if you consider the locally compact abelian group, this usually is 1. Because for finite abelian group, this is 1. But here, it depends on the quantum dimension. Okay, depends on this quantum number. So that means this is quite different from the classical case. Yeah, that is what I want to say. And we also can characterize this extremism. Okay, that means we know that this inequality is true. Then we can change the product. Actually, there's another product here. The usual product is the multiplication of this in this algebra. But the other product is the Fourier transform of the product from the other side.
How does your theory, physical theory, depend on this n?
Which one you mean, the n series?
So the idea is that you have many inequalities.
Yes. That is up to the structure. Yeah, because for the index less or equal to 4, the structure is completely determined. Yeah. So actually we have a lot of structure here. For the class case, we only have R, right? This is only one structure. Here we have infinite structure. Yeah. So that I will give this data. Okay, we will have this interchange of multiplication of convolution. And we will also have the quantum sure product theory. And for the commutative case, this is trivial. But for non-commutative case, this is highly non-trivial. Because it also includes the sure product theory. And you see that for matrix, we have sure product theory, and that is non-trivial. Okay. So in some sense, we unify the cases, the class cases and the matrix cases. And we also have this Yanqi inequality. And the coefficient also determined by this quantum number. But we don't have good reverse Yang inequality now because it's non-commutative. It's hard to handle. So once we get the extremism of this inequality, actually we get some analog of Gaussian inequality, the Gaussian function, right? So we have this bishift of biprojection. And we say that the bishift of biprojection actually is the extremism of Hausdorff-Yang inequality, the extreme power of Yanqi inequality. So it's quite analogous to the Gaussian functions. It's natural to get this biprojection because if you have projection, you can take the Fourier transform. You would like to ask what is transform would like to be. The simplest way is to require it to be a projection, right? Here we cannot require it to be projection directly. It will become a multiple of projection. So actually we have a lot of similar notations like bi-unitary, bi-positive, bi-invertible. Okay, and especially for bi-unitary, it's very important to determine the structure of this subvector. But here, we only want to discuss this biprojection. If we consider the classical case, we say that the biprojection actually is similar to the subgroup. But for classical Fourier analysis, especially for finite abelian group, we actually have translation and motivation of this subgroup. Okay, then we will get the shift of biprojection and the bishift of biprojection. And if we take the convolution of an element and then take average, we will say that this converges. And it converges to a bishift or biposition. This is also quite similar to the Gaussian function. Okay. So this can be considered as a discrete central limit theory. I give the picture of this bišift or biposition here. It simply is the pullback of the projection from the dual side and the projection itself. Okay. So I introduced the fundamental notation in the quantum Fourier analysis, like Fourier transform, convolution, and the bišift or biposition. So what can we do it? What can we do for it? Currently, we have 4 directions here. We hope that we will have more. The first one is quantum inequality. When I say quantum inequality, this means inequality of quantum symmetries. The other one is the unitary categorification. This partially is talked by Sebastian Pelkos several months ago. Okay. And the third part is 3 output theory. This is also talked about by Professor Zhengwen Liu at ICCM. And I'm also will simply introduce this bimodal quantum channel, which generalizes the quantum channel in quantum information. Okay. So like Fourier like inequality, we already introduced the Hausdorff-Fourier inequality and the Yanqi inequality, right? But there are a lot of other inequalities, like Func estimation. Is try to estimate the support of the convolution of 2 projections. We can also try to estimate the convolution of 2 elements. Actually, usually is the states or density matrix here of the entropy of the convolution of 2 densities. By difference of the Hausdorff-Fourier inequality, we get the Hertzmann-Becker inequality. And by using Jinsong inequality, we will get Donald-Stark unreversible. And we can calculate the extremizers. We also have non-commutative hard-S unreversible. We know that for classical hard-S unreversible, if the function is bounded by a Gaussian function and its Fourier transform is also bounded by a Gaussian function, then this function has to be Gaussian function, right? Here we have a similar one. If one side is bounded by a bišift or biposition, the other side is also bounded by its Fourier transform, then this one should be the bišift or biposition. And for entropy, we can use the more general one, like reigning entropy. Also, the relative entropy will also get the uncertainty principles. We would like to generalize the Yanqi inequality, like Brass-Campbell inequality, Brass-Campbell-Lieber inequality. Here this is still in progress, because when we try to generalize the relation, we find that this is much trickier, because we are going to replace the linear functions to planar tangle, and the planar tangle is hard to deal because the relation here usually is non-commutative. But we will obtain a lot of partial results. Yeah. So like I said before, the bišift or biposition is quite important in our research. It is the extremizer of the Hausdorff-Fourier inequality. Okay, it's the extreme pair of inequality. Minimizer of uncertainty principle, extremizer of sunset, extremizer of entropy convolution inequality, exactly. Yeah. And it's also the limit of some kind of identical independent distribution. Okay. So there's also another notation called biunitary. Somehow there is similar role for this inequality. Like if we consider the maximizer of uncertainty, we will get the biunitary, not the biprojection. Okay. The second direction is about the categorification. Unitary fusion category actually is combined by fusion ring and Panic equation, which is also defined by this F symbol. We say that the unitary fusion category actually can be realized as suffix, actually realized as suffix Anal algebras. Then we can use suffix to study the unitary fusion category. In our case, we say that the unitary fusion category satisfies all inequality we introduced before. But you say that for fusion ring, this has less structure. An important question is that whether a fusion ring is a quadratic ring of a unitary fusion category. And usually this is not true. Then how to determine it? In general, in an algebraic way, they will consider the dimension, whether it is an algebraic integer. But here, we use a completely different way. And this way allows perturbation. This is important because for computer software, we can allow some perturbation, and we can do a lot of things. So we say that the quantum inequalities such as quantum sure product theory, Yang inequality are true for unitary fusion category, but for some inequality like quantum sure product theory, Yang inequality are not true for fusion ring. And it's easy to develop a computer program to run on this fusion ring. So we say that they produce powerful and efficient criteria for unitary categorization of fusion rings. Okay. And also, if we consider the dual of convolution, we actually get a complete positive map. Okay. But the complete positive map actually is not usually complete positive, especially for fusion ring. We will get this inequality, which is much powerful than the quantum sure product theory. Next, I would like to introduce a recent work about 3 output. Recently, we found that we have a new TQFT, which we call the output topological quantum event. It unifies numbers of topological moves, and it unifies the RT TQFT and the TV TQFT. It generates the higher genus for this sure indicator. And the Fourier transform here could be simple because we have a lot of colors can be defined here. The Fourier transform here is interchange the colors in the TQFT. Okay, so this is a very simple idea, but we can do more. And yeah, it changes the whole system. You have like we have this graph here. You have inside, you have outside, right? Then we can color them different. Then we can change the color, and then the whole thing is still a picture or maybe a topological structure inside. So it is the transform between the TQFTs. So I would like to say here, because I'm talking about the quantum Fourier analysis.
It's often the boundaries of these TQFTs, right? The Fourier transform.
Yes. Yeah. So it helps us to generate quantum inequality topologically. Like for this one, it is in algebraic way. But here, if we write it in TQFT, it has this topological way. The positive is from this side, because it's if you consider if you put the line here, you see that the upside and the below side are symmetrical. Okay. But here is you see that this is not symmetry. But from here, you see this is A times A star. Then this will give us the positivity. But here, you cannot read the positive here. But from left-hand side, we will get the positive. So when we write it this in the algebraic way, we will get this inequality. So that means we can use this topological way to generate numbers of quantum inequality. Actually, we are doing it, but the harder point is that it's not easy to write a simple expression on the right-hand side. Okay. But we do have a lot of inequalities. The last direction is about the bimodal quantum channel. The quantum channel actually is a unit of complete positive map, which plays a very important role in quantum information. Okay, this is in Heisenberg picture. We use the unitor. But in Schrödinger picture, it uses the trace preserving. Okay. A bimodal quantum channel is a quantum channel preserving a subalgebra. Here, usually we just preserve a von Neumann subalgebra, not just a subalgebra. But you may not know the von Neumann subalgebras or von Neumann algebras. Then I simply say this is subalgebra because usually it could be the matrix multiple matrix algebra. So for bimodal quantum channel, it's completely determined by its Fourier multiple. In the usual confirmation, this actually is called the Troy matrix. Okay, that means the subalgebra is trivial. For the general case, we have to use the surface theory. Here, actually, if we use quantum Fourier analysis, then this will interpret as Fourier multiple. And we establish the pair probability theory for this one. And we also can study the phase group of bimodal quantum channel. And this indicates that, and by our study, this indicates that this is essentially different from the usual quantum channels because the quantum symmetry actually involves. And the relative entropy for bimodal quantum channel is also well studied by Zhishuo Zhao, a student of Zhengwei Liu recently. And he obtained a series of nice results for this relative entropy. Okay, what should we do in the future? From 4 directions, we would like to obtain more quantum inequality. Like we can use the classical way. The classical way actually is the analytical way. We can use the differentiation or compare with operators because there are a lot of techniques from the operators algebras and classical series. And here we actually have another way. We can use the topological way because this quantum inequality actually has meaning in this TKFT. And by using TKFT, we can simply draw some graph to obtain some inequality. Okay. And the usual Fourier transform can be viewed as interchange of 2D colors, as I drew before. When I draw a box, we're actually on the plane. Yeah, the string can goes to infinity anyway. But for 3-dimension case, this color is quite different, right? Because the range actually is not just in plane, actually it's in S3, right? And we can go further, like S4, S5, higher sphere, but we don't know because it's even harder for 3-dimension case. And this is going to collaborate with Shuai and Wang from DIMSA. We will also develop infinite dimension quantum information via bimodal quantum channel because the underlying quantum system will be infinite. Okay, this will be collaborated with Zhishuo Zhao, etc. So what other possible directions. We know that there are a lot of connections between the classical Fourier analysis with the other field, but we're still searching for other possible direction for our quantum Fourier analysis. So everyone is welcome. Thank you.
Okay, questions?
You have before for Fourier transform is something that all this definition of generalization of before was done, yes? Because you have different manifolds, some finite manifolds, continuous manifolds, and then you have completely different definition of the Fourier transform, right?
Actually, our definition actually inherits includes the classical definition. Actually, for finite abelian group, it actually contains the usual one. It also considers some Fourier transform from the category theory like symmetries. So even for R, we actually contain it, but it's not in planar algebra way. Actually, if we use locally compiled quantum group, that setup, then we actually generalize that one. Yeah. But for that part, the point is that we cannot derive the usual Hausdorff-Yang inequality directly. We can only obtain the true one. That is also a big problem in the theory of quantum group. I mean infinite quantum group, because they want to try to find an example such that this example is different from R, and the Hausdorff-Yang inequality is non-trivial from R. And they try a lot of such kind of case, and they will have. That is why they develop a lot of Yang Fourier transform, like a local transform or like a fraction Fourier transform, exactly. Yeah.
More questions?
Do you know of any like sheaf theoretic interpretations of the quantum Fourier transform? For instance, we have in algebraic geometry like the Fourier-Mukai transform as the analog for sort of this classical Fourier transform. So is there something exist in the quantum analog?
Actually, I don't know about algebraic geometry, but our Fourier transform actually generalize a lot of duality in this category theory. I know that category theory actually applies this algebraic geometry. So I believe that there should be something in this algebraic geometry. So maybe we can discuss about later.
I think using kind of simplified bundles and so on, your Fourier transform can definitely be written as a Fourier-Mukai transform, first of all.
Okay.
But actually, interesting thing for me, which is related, I was going to ask, that's a good question,
great.
Is that this quantum inequality really depends on your choice of Fourier kernel.
Yes.
So in the categorification, the other direction is you perturb the kernel.
Yeah, actually, this inequality is very sensitive to this structure. If we have the structure is not that restrictive, the inequality will be changed. Yeah, like a spin model. If you know the specular has the less quantum symmetry inside, then this inequality is not written in this way. Actually, it's somehow trivial. Yeah.
So maybe a quick question. This couple of days ago, I was in Zheng Wei's talk in Shanghai. So I'm wondering, this quantum inequality, what does it imply for WRT invariant?
I don't know that. Maybe we can.
Does it even exist there? Because in the case of WRT invariant, to my understanding, he starts from some quantum half algebra, looking representations on it, and he constructs this infinite series, which is actually over some quantum ring. But this inequality you're saying exists in that, this alterfold theory seems like suggesting that this inequality can kind of exist there. if you have a link with two boundaries.
Yes, I think so. Yeah. I am not familiar with that. The W2. What is that W2 theory? Okay.
Yeah, it's interesting because this doesn't exist in that realm, but it's very interesting. Any more questions? Okay, if not, let's thank him again.